Hello everyone. In this video lecture, we are going to study about the fundamental steps in digital image processing. I am Dr. Inbamalar, working as professor in the Department of Electronics and Communication Engineering, RMK College of Engineering and Technology. Now, let us coming to the fundamental steps in digital image processing. The basic and primary requirement is image acquisition, which means capturing of the image. So this image acquisition is the first process. This can be defined as the act of procuring an image from the sources. So this requires hardware systems such as cameras, sensors, etc. So coming to this image acquisition, see, fundamentally we will be having an energy source. That energy source will be producing energy and that energy will be made to fall on the scene to be captured. Now, this energy can be absorbed by the scene or reflected by the scene or transmitted by the scene. So there is a setup to capture the energy. Now this energy will be applied to the sensor. The sensor will be converting this energy to electrical energy. Now this electrical energy will be analog in nature and we will perform two operations, sampling and quantization, to convert this analog image to digital image. So the digital image can be further processed using a digital computer. This is fundamentally image acquisition. Now, next let us move to image enhancement. So the image processing, fundamentally it has to convey some information and it should be visually appealing. So now image enhancement is the simplest area of digital image processing. The fundamental idea behind this technique is to bring out the detail that is obscured, or in other words, to highlight certain features of interest in an image. So when we take the common example, we can increase the contrast of an image to make it look better. This is an example for image enhancement. So this basically improves the visual appearance. So now increasing the contrast and fixing at a particular level is depending on the user. Whoever views the image, if they feel it is looking better, they will stop in that position. So when we consider this enhancement, this is a subjective area. The user is making a subjective decision. So there is no mathematical models involved. It is purely based on the human being who is doing this task. Now let us see this example. The left one is the normal image and the right one is the enhanced version of this input image. See, other example. So the image available is shown 3 varieties of enhancement. So now depending on the user, subjectively the enhancement quality of the image is decided. So that is what it is called, subjective decision. So now let us move to the next one, image restoration. This is also fundamentally doing enhancement task, which means this also improves the appearance of an image. But unlike enhancement, here this is using a mathematical model, which means this is not a subjective decision. This image restoration is objective in the sense that the restoration techniques are based on mathematical model, generally probabilistic models of image degradation. So, degraded image can be enhanced to convey some information in the case of image restoration. So this image degradation, how it is caused? This can be due to improper opening and closing of shutter in the case of a digital camera, atmospheric turbulence, misfocus of lens, relative motion between camera and object. So these are all the common examples of causes which produces a blur image or degraded image. Now restoration restore the original image from the degraded image. So let us see example. The left one is the degraded image which is too much of blur, and the right side is the restored image where you are getting the information. Another example for the degraded image and the corresponding restored image. So this is regarding image restoration, and now let us move to color image processing. So color image processing, basically the image processing what we describe in theory will be gray level processing. And color image processing needs color image models, and this is an area that has been gaining importance because of the significant increase in the use of digital images over the internet. Next, let us come to the next concept, wavelets and multi-resolution. So wavelets are the foundation for representing images in various degrees of resolution, which means multi-resolution. So here wavelet, which means a small part of the wave. Let corresponds to a small part. So wavelet, a small part. Here the images are subdivided successively into smaller regions. That is why this is called wavelets. This represents various degrees of resolution. So this is called multi-resolution. So let us see this example. We have our original image 256 cross 256. This is subdivided into low, low, high, high, low, high, high, low. So this low, low will be low frequency components. This high, high will be high frequency components. Low, high and high, low in between. So the image is subdivided. Whichever component, whether it is a low frequency component, if you are interested, you can further subdivide it. If it is a high frequency component, you are interested in further processing, you can further subdivide it. So like this, you can go on analyzing multi-resolution. And now we have a transform called wavelet transform. So the original image, if you take discrete wavelet transform, you will be having wavelets, and the reverse for the wavelets, if you take inverse discrete wavelet transform, you will be getting the original image. Next technique is compression. Compression basically required for reducing the storage required to save an image. Also this is required to save the bandwidth required to transmit it. And coming to image compression, there are various techniques available which makes the files smaller while retaining high quality. And the standards available, one example is .jpg file, which is the standard of the Joint Photographic Experts Group. Example, original image, compression ratio 10:1. Another image, compression ratio 45:1. You could see lower compression ratio, more closer to the original image. Next, let us see morphological processing. Morphology deals with the representation and description of shape. So, morphological processing deals with the tools for extracting image components that are useful in the representation and description of shape. See the examples. See, the first one is dilation, the second one is aeration. So, these are the morphological image processing operations. Now let us move to the next one, segmentation. Segmentation, partitioning an image into its constituent parts or objects. This technique partitions a digital image into discrete groups of pixels, image segments to inform object detection and related tasks. So, here depending on the segmentation, whether it is weak or erratic, the quality of the processed output. In general, the more accurate the segmentation, the more likely recognition is to succeed. Example. Next, let us move to the next one, representation and description. Representation and description almost always follow the output of a segmentation stage, which usually is raw pixel data constituting either the boundary of a region or all the points in the region itself. So, in either case, converting the data to a form suitable for computer processing is necessary. The first decision that must be made is whether the data should be represented as a boundary or as a complete region. So, we have fundamentally two types of representation. One is boundary representation, other one is region representation. So, if you see this example picture, you could see the left one is boundary representation where you have only two gray levels. The boundaries are represented by the one gray level and the region represented by another gray level. So, coming to this region representation, you have used different intensity levels to represent the regions. So, boundary representation is appropriate when the focus is on external shape characteristics such as corners and inflections. Region representation is approximate when the focus is on internal properties such as texture or skeletal shape. Choosing a representation is only part of the solution for transforming raw data into a form suitable for subsequent computer processing. A method must also be specified for describing the data so that features of interest are highlighted. Now let us come to description, which is also called feature selection. Description deals with extracting attributes that result in some quantitative information of interest. These are basic for differentiating one class of objects from another. Next one, recognition. Recognition is the process that assigns a label to an object based on its descriptors. Study of how machines can observe the environment, learn to distinguish pattern of interest and make reasonable decisions. So, if we consider humans, they can recognize objects within a fraction of a second. As number of expected targets become larger and larger, it becomes difficult for human observer to identify an object from images of poor quality. So now this is the example, region of interest, analyst, and it is classified as good or faulty. Next one, knowledge base. Knowledge about a problem domain is coded into an image processing system in the form of a knowledge database. This knowledge may be as simple as detailing regions of an image where the information of interest is known to be located, thus limiting the search that has to be conducted in seeking that information. The knowledge base also can be quite complex, such as an interrelated list of all major possible defects in a materials inspection problem. Hope you understood this topic. Thank you.